A very good afternoon to everyone. Let us begin the session with our esteemed Chief Guest, Professor Israel Cohen, sir. He will delivering the lecture on Introduction to and Overview of Array Signal Processing as well as Fundamentals, and brief overview he will give you. And his delivering lecture will be continuation before this. Well, I invite our Professor Israel Cohen, sir. Please come onto the stage and deliver the lecture, continuation of the yesterday's speech. Thank you, sir.
Okay, thank you. Good morning. Just a minute. Let me turn off Wi-Fi. Okay, so yesterday, first, do you have questions? Okay, so even if you have questions about what we talked yesterday, you can just interrupt and ask questions. We will continue from the same place. Yesterday, we talked about array gain and directivity factor. Okay, so array gain is actually the improvement in signal-to-noise ratio of using the array beamformer compared to a single sensor. Multiple sensors anywhere in space. Okay, so we can call any one of the sensors as number 1, and then we can count them 3 and so on until we have m sensors. So usually we have here m inputs. We multiply each sensor signal with some weight. So here we have certain weights. Let's call it W. And then we have here the beamformer output. We will talk about more, but usually what we take the signal that is received in each one of them, 1, Y1T, and so on, Y2T, and so on, all of them. So the output, if we call it ZT, is actually can be written as a summation of taking the weights. If we talk about filters, so each one will be like HIT convolution with YIT. These can be the weights, the filters from I equals to 1 to M. Or we can write it in the frequency domain as ZF, summation from I equals to 1 to M. We can call it WF, so it will be some weight, YIF. So this is like superposition of the signals that we measure by the sensor array. And then suppose that the signal-to-noise ratio is the same for all the sensors. So we can define as on one of the sensors input SNR. So it will be relevant to one of the sensors. Let's assume that the signal-to-noise ratio is the same for all the signals. And we can define the output signal-to-noise ratio here. So it will be output SNR. So the ratio between output SNR and input SNR, we call it array gain. So it will be output SNR divided by input SNR. So this ratio is actually the same as what is the gain that we achieve for the desired signal compared to the gain which is a result for the noise signals. Okay, so it's the same. It's the same. Because we have some gain for the desired and some gain for the undesired signal. Yes?
So here we assume the inter-element spacing to be less than lambda.
Actually here, I don't assume anything about the configuration of the array. It doesn't really matter. And after the output, suppose that I have certain weights or certain filters. I get output here. And because it's linear, this is a linear beamformer. Beamformer, it means that we have some weights or some filters. It's the same, the frequency domain. So here we get some output SNR. We can write the output as summation of two components. One is desired, one is undesired. Okay? And the desired, the power of the desired compared to the power of the desired in one of the sensors here, there is some ratio. This is the gain of the noise. We have also what is the noise here compared to the noise in a single sensor. This is the gain of the undesired, the gain of the noise here. So this ratio is actually the same as output SNR divided by input SNR. Okay? So we want this to be as high as possible. So we have more gain in SNR. But when we measure that, so this is called array gain. But the array gain depends on usually depends on the noise environment. So we said that if we define this for white noise, especially white noise, we call it white noise gain. So we call it white noise gain, which means what is the array gain when the noise is spatially white, which means that the noise is a thermal noise, which is independent in any field, any sensor. And another definition is directivity factor, which means what is the array gain when the noise is diffuse noise. It comes from all directions with the same power. So these are definitions. And generally, if we have this array gain. We obtain it. This is the directivity pattern. So the directivity pattern for a certain direction, this is the direction of the desired source. The magnitude squared of the directivity pattern in the desired source direction, it means this is the gain of the output desired signal. And if with the same power, so if we take the three-dimensional, the integral on a sphere of the directivity pattern, the magnitude squared of the directivity pattern of noise. So we can define this as the directivity factor. Sometimes we want to maximize the directivity factor in some way. Okay, so how we change this formula, how we change this when we have a near field source. expression was obtained when the distances between sensors is ND.
Laptop
Okay,
చాలా
so
slow ఉంది.
inter-element distance
చాలా
is
slow
D.
ఉంది.
And we have elements from
చాలా
minus
slow ఉంది
n minus
laptop.
1 divided by 2 to n minus 1 divided by 2.
పోతుందా అలాగే
So we have n elements, and we assume that it's symmetric, but it doesn't have to be. This expression is for correct. So we need to change this, the distance, by this distance, because this is more general for spherical spherical waves. If we replace the spherical wave by plane wave, we get nd cosinus phi. Okay, so it will be between the first the reference sensor but we need to take into account also the decay of the acoustic wave. So the decay of the acoustic wave here, so we take that also into account because it decays according to the distance. So without the wave, this is actually the acoustic wave that hits the sensor, the emit sensor, compared to the reference sensor. Here we call it number 0. So this will be the directivity pattern for near field source. So any near field source at the output,
Stuck in.
what do we mean
Laptop stuck
measure?
in.
What do we measure?
Laptop stuck in.
Directivity pattern, what does
Well,
it
it's like-
say? That any, or the near field, that any source that is at a certain position,
ఎట్లా
we can call it at a certain position, r, theta, phi. Or we can assume that theta is in a different place.
కనబడే
but
కనబడే
We can assume that we have a certain
చూసుకో.
position
చూసుకో.
of the near field
అది
source.
చూసుకో అన్న
For far field, we don't need to specify r, the distance, because it's far field. But for near field, we need to specify r in addition to theta and phi, the direction. This is the direction, this is the distance. Okay, so what does it mean? At the output of the beamformer. Certain weight, and we take impinges all the like this. So this sensor number 0. Here we have 1, 2, and so on. 3, minus 1, minus 2, minus 3. With and then we take all these outputs into account. So we take their summation, and here we have the output. So we ask ourselves, suppose that the source is in a certain position in space, and we get the signal here, what will be the strength of the output? So this is the directivity. And we can normalize it, of course. We can normalize. So if we divide it by a certain value, it doesn't really matter. So we can normalize. And this summation is the strength of the output signal for near field. So now we want to see what is the difference between far field directivity pattern and near field directivity pattern. So this is just an example. So we saw that for uniform linear array, the far field directivity pattern, it goes like, you see, it has some zeros, okay? It's a Dirichlet function, okay? So it has some, it means that for some directions, we have nulls. So with far field source that comes from a certain direction, from this direction or this direction, we will not get any signal at the output, because all the signals that come to all the sensors, and by the way, in this case, we have specific values, okay? So this is the far field, the blue line, and it comes from a certain, the direction is here. We assume that theta is pi divided by 2, 90 degrees. And for a certain frequency, 1 kilohertz, we have 11 sensors, and the distance between sensors is 0.1. Okay? So if we take the weights constant, 1 over the number of sensors, it's constant, we will get this directivity pattern. So we say it's maximum for the signal that comes from 90 degrees, from the broadside. Of course, because if the weights are all constant, let's say it's 1 over n, and the source comes from far field from the broadside, and we accumulate all the signals that hits all the sensors, we will get the summation that it's maximum. That's why the maximum is 490 degrees. And of course, we can normalize it to 1, okay? And for certain directions, the summation can be cancel each other because they have different delay. And then we have cancellation of the signals, and then for certain directions, it may be 0. And for some directions, it's much smaller than the 90 degrees. But for the near field, suppose that we put the source is 1 meter away from the array on a circular, because we take 90 degrees. We just want to see the variation versus phi, the horizontal direction. So you see that the near field directivity pattern goes like this. And of course, we can also normalize it to 1. It doesn't really matter, because what we care about is the differences between different directions. So we see that for this near field source, it doesn't go to 0. So for any direction, because you cannot cancel exactly. Why do you think we cannot cancel exactly in this case? So we have 11 sensors. What do you think? What made this situation that you cannot cancel the source that comes from any direction? The summation of the signals with constant weight, they cannot cancel each other. What do you think? Because we have two differences between near field source and far field source. What are the differences? Yes, it's spherical. So the differences is in the phase. Okay? So in the phase. So it doesn't go like something like horizontal. So the differences in phase between two sensors are different than far field. But also the decay, the magnitude. So these two factors, especially the decay, because the decay depends on the distance, make this near field directivity beam pattern such a way that it doesn't cancel. Okay. So now I want to ask you a question. Is it possible to have a null here by changing the weights? The weights, this is the result of the directivity pattern when the weights are all constant. All the weights are simply 1 over n. Okay? WIF equals to y over n. So the question is, can I change the weights? The weights are complex in the frequency domain. Can I change the weight such that I will get for a certain direction null? Is it possible? Yeah, it's possible. Is it possible to change it that I will have 2 nulls? 2 nulls for 2 different directions. Is it possible for 3 nulls? And so on. How many nulls can I get? Is it possible to design it in such a way? So these are questions that we will ask. So when I say that we want to change the weights to get a beam pattern, near field, directivity pattern and beam pattern is the same. Okay? So if I want to get a different directivity pattern, desired directivity pattern, by changing the weight, this is called beam forming. Okay? And we will see how to design beam formers. But not only that. So when I design beam formers, I can ask myself, maybe I can change also the location of the sensors. So I can change the number of sensors. I can change their location. It doesn't have to be on a line. I can change it to be anywhere. How do I design sensor array? Where to put? How many sensors? Where to put them? And so on. And then I need to design the weights such that I will get a desired either far field beam pattern or near field beam pattern. It depends if the source is in the near field or far field. Okay, and another thing that I want to emphasize, that when we took this equation, okay, so the near field, you see that if I go back to this equation, you see, so this is the directivity factor that was obtained for far field. So if you want to change it to near field, you just need to change here. Here you don't change. Here you take the directivity pattern of the far field. And the question is why? So if this is the array gain for far field, what we saw before. And now we saw that we need to change the directivity pattern is different for near field. So if we want to compute the near field array gain, what does it mean array gain for near field? That the desired source is in the near field. But the noise comes from all directions, so it's still the far field. So when you change this formula, this expression, you don't change the directivity pattern both in the numerator and denominator, only in the numerator. Source is in the near field, but the noise that comes from all the other directions is the same as the far field. So here we don't change it, which is important. Important to understand this. Okay? Any? The array gain depends on what? It depends on the, no, of course, yes. This is the array gain, what we saw, this expression is for the far field sources. So that's why here it doesn't depend on R. But I agree with you that if we compute the array gain or here, directivity factor. So if we compute the directivity factor for near field source, it will depend also on R, the distance of the source from the array. But we need to change the directivity like we used for the near field only here in the numerator. In the denominator, it will be the same expression. Okay? So we change here in the numerator, we need to use this expression. You see? This expression. And actually, I agree that here it needs to be also a function of R. So it's missing here. But it needs to be as a function as R, because you see it depends on R. I will add it. Anyway, this expression you use only in the numerator of the directivity factor, not in the denominator. In the denominator, you put here the far field. So it will cancel here, and here you will get nd cosinus phi. Okay? Any other questions? Yes. Okay, white noise gain. So if we take the white noise gain, what does it mean? So it's a good question. Actually, we will talk about it. You see, so how do we change the array gain for white noise? So we don't use this denominator. It will be different because actually we don't take noise that comes from all other directions. So we will see how to modify this. The denominator is the same, okay, because this is the gain for the desired source. So either near field or far field. We change only near field or far field in the numerator. In the denominator, if it's diffused, it looks like that. If it's not diffused, you need to change that because it depends on the noise. We will see. Okay, we will talk about it. Any other questions? Okay, let's move on. So we understand how to change things, how to modify for near field. Okay, so let's talk about beamforming techniques. Beamforming, it means that we want to design these weights according to some specifications or desired features. How do we do that? So we will talk about classical beamformer, maximum directivity beamformers, because sometimes we want to design these values such that the directivity factor will be maximum. And this part I will skip. The generalized side lobe cancer is an adaptive beamformer. We will talk about when we reach adaptive beamforming. So I will skip that for this overview. Okay? So in order to talk about beamforming, how to design these weights, we need to talk about noise fields. So we already talked about noise field. We talked about spatially white noise. We talked about diffuse noise. And also we have sometimes directional noise. If a noise source comes from a certain direction, it's called directional noise. And of course, in practical environments, it's combination. It's more complicated because we have some surfaces, the noise hits some surfaces and propagates with a certain transfer function and so on. But the simplest or the standard simplest noise fields are three types. Okay? First, we have coherent noise. Coherent noise, so we define it according to the coherence of the noise that is received in two sensors. Suppose that we have any two sensors, sensor I and sensor J. So here we have the cross-spectral density between the signals, between the noise signals in the two sensors. And we normalize it by the square root of the autospectral density of the noise that it received in sensor I. And this is the spectral density of the noise that is received in sensor J. So we can, this is definition of coherence of signals between two sensors. So if we measure the magnitude squared coherence, we take this value and we take the magnitude squared, so it's always between 0 and 1. So for coherent noise field, it means that the magnitude squared coherence between any two sensors is very close to 1. So this is obtained when we have a noise source or interference without any reflections. So if we have a noise source and we don't have any reflections in the environment, it hits or it is measured by each sensor by simple delay. Okay? So we see that if we have a simple delay of signal between every two sensors, so if you take a sensor and another sensor, and the relations between the signals in the two sensors is simple delay, we have magnitude squared coherence which equals to 1. Okay? So in free field, or when the walls are very far, so reflections can be neglected and so on, or in anechoic chamber, for example, for acoustic waves, or in the air, if you have electromagnetic waves and it hits without, you can neglect reflections, you will have magnitude squared coherence which equals to 1. you want to put a sensor array number of sensors because it requires more. Suppose that I don't tell you what is the desired beam pattern. I just tell you can I design these weights? Can I design these weights such that the man will be for a certain direction? Yes. Now, suppose that not only that I want the maximum to be in a certain direction, but I want the directivity factor. What is the directivity factor? The maximum here divided by the integral for all the directions. I want to maximize it. So I want to design these weights such that the directivity factor, the ratio between the maximum and the integral, will be maximum. Is it possible to do that? Yes. You see, maximum directivity beamformers are very important. Why? Because sometimes you don't like to design that I put design. We just want that the beam width will be constant in frequency. Sometimes we want that the position of the nulls, of the position of the nulls or the side lobes will also be independent of frequency. So we call it different, we have different names. If the beam pattern doesn't change in frequency, we call it frequency invariant beam pattern. If only the beam width remains the same, is independent of frequency, but the side lobes may change for different frequencies, we call it constant beam width, beamformer. Okay? It depends what we like. So when I said that for high frequencies we don't want to distort the signal like a low-pass filter, it's enough that the beam width will be constant. So you don't want to add more constraints if they are not necessary. But if it's important to keep the null, for example, you know that the null for certain frequencies, for a certain direction, it depends on the frequency. So suppose that there is a source that comes from a certain direction and you want to put null. This is called also null beamforming. And you want that it will remain in the same direction for all frequencies. And maybe you don't know, but you want to keep the side lobes the same, independent of frequency. So it's possible to design, when I said design beamformer, it means how to design these weights. So it's possible to design it such that the beam pattern will be frequency invariant. But of course, you add more constraints. If it's not unnecessary, then don't do that because it limits the performance. You know, in mathematics and optimization, when you have constraints, you pay for that. You pay for that with the performance. So the more constraints that you have, it lowers the performance because you have the constraints. Or you need to pay with that with additional hardware, additional software. When you have more constraints, you pay for that. Performance, hardware, software, whatever, complexity, and so on. So try to take the minimal constraints that you actually need, always with optimization. Maximum directivity beamformer. So I talked about when you want to maximize the directivity, this is the directivity of the beamformer. So this is the expression that we got for far field. If it's near field, of course, we need to change in the numerator the beam pattern for the near field source. Okay, so this is, we will talk about it maybe later. So how do we maximize this? What do we mean? We maximize. We need to choose the weight, the beamformer, such that this ratio, this is the array gain for diffuse noise, which is the directivity factor, will be maximum. How do we do that? So when you want to maximize something, the first thing in mathematics, optimization, is to write it as a function of what? Of the parameters. So we need to write this array gain, this directivity factor, as a function of the weights. How do we do that? So we can write the directivity pattern as a function of the weights. How do we do that? You see, the directivity pattern is written like this for far field source. And far field, and when you see it here, what does it mean? If I write it like this, this is the phase differences between sensors. So it means that we used uniform linear array. Okay? But actually, I can get something similar for any configuration of the array, but for simplicity, we use here uniform linear array with the inter-element spacing, which is D. So we can write this like this. W transform conjugate multiplied with D. So in a vector form, it looks like this. So this summation, in a vector form, it looks like this. So we can write the directivity factor as a function of the directivity pattern using the weight vector that we multiply each sensor. So we have a weight vector, and also the integral, we can take it out, and the integral over this vector. If I go back, you see, this vector is called the propagation vector or the steering vector. Actually, what does it contain? It contains this value, the phases that come or measured that are obtained with each sensor. So the integral here, it doesn't depend on the weights because we took the weights out of the integral. It's not dependent on the weights is what we want to find. It's independent of the direction, but D depends on the direction. So we can compute this integral in advance. And now we can write it like this. By the way, we can compute this integral, you see, which is for diffuse noise. So we can call it, this is a matrix. We can call this matrix, we can write it as gamma, okay? And actually we know exactly how to find this gamma. So we have this ratio, you see? So this was the first stage. We want that the directivity which we want to maximize, we wrote it as a function of W and other things which are independent of W. But we know them. This is the steering vector or propagation vector for the desired direction. And this is gamma, which we know how to compute. So how do we maximize this? So we can, of course, maximize this. Is it sufficient? What does it mean that we maximize this? It means, by the way, I didn't write here the dependence on the frequency. We maximize this, we maximize W, we maximize the directivity by using W for each frequency. Okay, so this ratio depends on the frequency. Okay, but I didn't write it for simplicity of notation. Okay, so this directivity, you see that the numerator is the gain for the desired source, and the denominator, what is the gain for what? Diffuse noise. And we want to maximize this ratio for each frequency. We can do it independently for each frequency. Now, suppose that this ratio is high for a certain frequency. Is it sufficient? So it maximizes the directivity for that frequency. But also what we want, very important, that the gain, the numerator, will be independent of frequency. Why? Because if it depends on the frequency, it means that we have different gains for the desired source for different frequencies. So this is a distortion. It's like distorting the desired source. So what we need to maximize WH for frequency, okay, over WF, D, and it depends on the desired source direction, okay, say like this, divided by WH F gamma F W. Okay? But we also need to put a certain constraint that the desired source gain will be independent of frequency. So it's subject to WHF DF PFS theta FS this any constant, if it equals to any constant which is independent of frequency, it's fine. I don't care about the constant. So I can write it as constant equals to 1 because it's independent. I don't care if this constant will be 2, 3, whatever. This is just a gain for the desired source. But it's important that this constant will be independent of the frequency. Okay, so you see it here. You see it here. So if it's 1, so the numerator is 1, so I need to minimize the denominator. I need to minimize the denominator subject to the same constraint. It's the same. See? So this is the problem of finding the maximum directivity beamformer. So we can solve this. How do we solve this? You see, this is a vector. I need to find this vector, which minimizes this. And by the way, you can put here any matrix Q. If Q is the cross spectral density of the noise, so actually we'll maximize this ratio, this array gain for any type of noise, for a type of noise that is characterized with this cross spectral matrix Q. If I put here gamma, it will maximize the directivity. Okay, so suppose that I know, what does it mean here? It's the cross spectral matrix Q for any noise. So if suppose that I know exactly the noise, I can measure it. And I can measure the correlation between noise signals in different sensors. So I suppose that I can find this matrix for specific noise. And I maximize this. So this is called minimum variance distortionless response. Minimum variance distortionless response. This is the distortionless response because it doesn't distort the desired source. So this is the constraint of the distortionless response. And minimum variance, it means that it minimizes the gain for the noise. So it minimizes the denominator, minimizes the gain, the average gain for the noise, and we have distortionless response. So this nominator is constant, independent of frequency. So this problem, the solution to this problem is called minimum variance distortionless response beamformer. And if instead of Q we put gamma, what we had before, gamma, which is suitable, it's the same matrix, but it's suitable for diffuse noise, then how do we call it? Instead of minimum variance distortionless response, it will be called maximum directivity beamformer. Okay? So the solution for this problem, the weight, you see this is the solution, Q minus 1, D, DH. So D is what we have here. This is D. For the direction, this is the propagation vector or steering vector for the direction of the desired source. And Q, we assume that we measure it or we estimate it. This is the solution. Note that the numerator is a vector. The denominator, what is it? A scalar, yes, because you see DH, Q minus 1, Q is a matrix, D is a column vector. So this is a scalar, it's just a scalar. How do we obtain it? So I give you some exercise, okay? The exercise prove that the solution to this problem using Lagrange multiplier, okay? Prove that this is the solution. Obtain this solution. By the way, if I substitute this into the constraint, okay, WHD. So I get 1, okay? WHD is the same like DHW. DHW equals to 1. So I actually, this solution satisfies the constraint. If I put here DH, actually it's 1. But also you need to show that it minimizes. So don't just use it. Prove that you can obtain this expression for the MVDR. And one of the problems of MVDR and also maximum directivity factor is that the white noise gain, when we try to maximize the directivity or we find the maximum minimum variance distortionless response, we get very low white noise gain, which means that the gain for white noise, you see here, if the gain for white noise, if we put here in this matrix, we put the identity matrix. See, instead of Q or gamma, the gain, the white noise gain, okay, of the array, it will be WHD magnitude squared divided by WHW. So we put here identity matrix. So this is the array gain for spatially white noise, for thermal noise. And as I said, we don't want that this will be too low. for any frequency. So we need to limit that this will be larger than a certain threshold. So this is the minimum acceptable threshold. If it's, for example, minus 20 dB, it means that we allow this threshold, we allow that the beamformer will amplify the thermal noise by 20 dB. So it means that the sensors, the thermal noise in the sensors is not too high. Okay? So it's not enough to formulate a problem like this, maximum directivity or minimum variance distortionless response beamformer. Usually, in practical cases, you need to add another constraint. So this will be the additional constraint, that the white noise gain is larger than a certain threshold. Sometimes this threshold, maybe it's independent of the frequency. Sometimes maybe you want to depend it on the frequency, but usually maybe you can put here a threshold that is independent on the frequency. It means how much thermal noise you can allow to amplify at the output of the beamformer. So what will be the solution if I add this additional constraint? It will be like this. So I can add several, instead of just one constraint here, I can add several constraints. So this is called linear constraint. For example, you see what I write here, that I want constant gain for a certain direction. Maybe I have other directions that I want to keep nulls in that direction. So maybe I have other constraint, for example, WHF, DF for certain other direction, maybe phi1, theta1. Maybe I want to put here 0 or any other value, 0.1 or something like that. But if I have a few constraints, I can put these constraints, I can write it like this. I can write it like this. So I can write the linear constraints so instead of this constraint, D, I can write it as DH F theta 0 phi 0 DH F theta 1 phi 1. So this is different directions and so on until we have a few theta P phi P. So suppose that I have, you see each vector here now is a row vector. So this is a matrix. And this matrix, we call it CH. Okay? And if we multiply it with the vector W, we get certain values. So for this, in the first value, it will be 1. The other directions, maybe we put zeros. Maybe we want, maybe we know that for other directions we have interferences. So we will put zeros in the other directions. So suppose that we want to solve to minimize this denominator subject to this constraint, the linear constraint. So this is the solution, and we can put epsilon, some epsilon here, which is larger than 0, such that it will also satisfy the constraint and the white noise gain. So the white noise gain will be higher than a certain threshold. So this solution is called robust LCMV, linearly constrained minimum variance beamformer. Okay, why is it called, why does it, we call it robust? Because we also have a constraint on the white noise gain. So how do we change it to near field? What do you think? How do we change it to near field? Everything that we saw here. So we saw a few things. We saw MVDR. Minimum variance distortionless response beamformer. MVDR beamformer. We saw it. We saw maximum directivity factor. Max directivity factor beamformer. We saw LCMV, linearly constrained minimum variance with the matrix C. So if we have more than one constraint and one direction, if we have additional linear constraints using this matrix of constraint, we call it linearly constrained minimum variance beamformer. And for all this, and actually we have more beamformers, for all this, we can add an additional constraint that the white noise gain will be higher than a certain threshold. If we add constraint that the white noise gain will be higher than a certain threshold, so all this will be robust. So we call robust MVDR, robust max ADF, robust LCMV. Okay? Understand that? We have additional beamformers. And now, if we change this, instead of far field to near field, what do we need to change? Okay, so let's go for the MVDR. What do we need to change? Only this. So the propagation vector, or the steering vector, which you call it here, we need to change it to near field. So the constraint that it's equal to 1, it will be with D that is near field. If we go to max DF, so instead of the matrix Q, it will be with the matrix gamma, which is relevant to diffuse noise that comes from all directions. So it will be robust, and we can add this constraint. So it will be robust max DF for near field source. If we have LCMV, so we take this matrix. Do we need to take everything here, near field or far field? So it depends. It depends on the sources. Okay? So maybe if it will be for near field, we need to put here R0, here R1, RP. Okay? So so it depends. If the source here, the desired source is in the near field, so it will be near field. If this source, we don't care about the distance because it's far field, so it will be far field. And so on. Okay, so we understand this. We understand how to define the problem of finding the optimal beamformer, and then we need to solve it. And the solution is quite simple. It's quite straightforward. What we showed before, you can also prove it. Any questions? So these are the modifications for near field sources. Okay. We assume when you put constraints like this, you assume that you know the directions if it's in the far field. But if you assume that the source is in the near field, you need to know not only the direction, but you need to know the position, which means the distance and direction. If you don't know, which is a good question, if I don't know, So one of the ways is to put a constraint not at a certain point in space, but on a region around it. Okay? So this is called region of interest beamforming. And if I have nulls in certain region, I can call it region of non-interest beamforming. Okay? So I can solve it instead for a certain position of the source, for a certain region, certain area of source, desired source or indesired or non-interest sources where I want to put nulls. I'll give you an example. Okay? So suppose that there are two loudspeakers here with music. I play one music, one song, maybe classical music, and one loudspeaker. And I put another loudspeaker here. I play rock songs, different type of music. So I put headphones on my ear, and I sit over there. Somebody else sits over there. And maybe we want to listen to different sources. I want to listen only to the classical music. And maybe somebody that sits here wants only to listen to the pop music. How do we do that? So I want, and I don't know exactly the position. So it's a region. So I want to maximize the signal that I received from the desired source, desired loudspeaker, without any distortion. Okay? So I want to constrain that with no distortion, I will get only the source from one loudspeaker, and the other loudspeaker, it will be suppressed as much as possible. It will be minimum. Okay? The power will be minimum. And then I can listen only to one source. And vice versa. So it depends on where is this. So I need to design it. Okay? I want to show you something. Where is like this? Just a minute. Okay, just a minute. Let me see here. Okay. Okay.
So you're wearing headphones?
Just a minute. Maybe I increase the volume. So I show you, maybe turn off the light here, here, or maybe here. Oh, oh no, sorry. Okay, good. Yeah, this is good. Thank you.
Create a sound bubble. When the sound bubble is on, then sounds outside of the bubble will disappear so that you can hear my voice very clearly. If you were at a restaurant, you can use a sound bubble to focus on the speakers at your table while everybody else outside of your bubble will be silenced.
So this example shows that somebody wears headphones like this, and he wants to talk to somebody and listen only to people inside the bubble. So they call it bubble sound. So he wants to listen only to sources inside the bubble, and people that speak outside or any sources outside the bubble will be suppressed.
It uses AI on the device to process audio from 6 microphones around the headband. And if someone walks into your bubble,
And you can hear them. You can hear them both, actually.
because we're both inside of the sound bubble.
And the sound bubble silences all the speakers outside of it.
We're evaluating the system. The system picks up the speakers that are nearby the user, and it will silence the people who are outside. If the system is working, then you should only be able to hear my voice, and you should be able to hear me clearly. We're evaluating the system picks up the speakers that are nearby the user, and it will silence the people who are outside. If the system is working, then you should only be able to hear my voice, and you should be able to hear me clearly.
Okay, so you see a nice example of sound bubble and how to design it. We'll talk about that. Okay. So we talked about this. Okay, so you see it's the same. You just need to change. You understand it. Okay, so we can skip that. I told you, generalized side lobe counselor or adaptive beamformer. We will talk about it when we talk about adaptive beamforming. Now I want to continue with single channel signal enhancement in the time domain. So we finished the overview of the objective. Now that you understand, so we can continue with more details. So single channel signal enhancement, it means that we have single source, single sensor, that the single sensor we have single sensor, we have the desired source and undesired. I will talk about the signal model and problem formulation, what linear filtering, performance measures, and optimal filters. Okay, after we have the overview, I think things can be much more quick to define this. You will see that for a single sensor, perhaps you already know some of the material, so I will go, it's more like definition. So when we move to multiple sensors, we understand the definitions and how to do that. Okay, so suppose that with single sensor, this is a single sensor, this is the measured signal. And suppose that we have two components. One is desired, one is undesired. And using this measurement, we want to estimate the desired signal. By the way, here, T is discrete. It's not continuous. Okay? So we have sampled signal. And we want to estimate a sample of the desired source. If I ask you something like that, you will not be able to estimate because you need more information. You need some information in order to estimate xt out of this measurement. So the question is, what type of information do I need? If I use only one sample of y, and I want to separate into two components, that is desired sample plus undesired sample, I don't think I can do that. I need to provide more information. So with linear filters, what we have is something like that. So instead of one sample, we can take a vector of samples. Maybe it's possible to turn on the light. So I can ask, okay, I want to obtain an estimate of xt. Let's call it zt. This is an estimate of xt. And a linear estimator, it means that I will use some samples of the measurement, and I will multiply them with a filter. So it will be like this. Summation from I equals to 1 to L, or let's say even from 0 to L minus 1. And then I take samples. Suppose that I want causal estimator. So it means that I take the samples from T minus I like this. So I have the recent L samples of the measurements. I will multiply them with HI, like this. So it's a superposition, a linear superposition of the recent L samples of the measurements. And the question is, how do I design these linear weights in order to estimate the sample at time t of the desired signal? So this is a linear filter. Of course, we can do it with nonlinear filters as well, but let's limit for simplicity our expressions to linear filters. Okay, so what do we do? We take L samples, L recent samples of the measurements. It's a vector y, and we want to use this vector in order to find these optimal weights. When we want to define optimal weights, we need to define what is the optimality criterion, which is important, and what is the information that we need in order to separate between the desired source, the desired signal x, and the undesired interferences, which are included in the vector, or in the signal v. Okay, so the minimal information that we need is a correlation. What does it mean, correlation? So this is a correlation matrix, okay? You see, I take the correlation for the vector y. So I know how any two samples in these vectors, how do they correlate? Correlation is on the average. Okay, so we have the expectation of y transpose. It's transpose because we deal with real signals. And it equals to the correlation because we assume that the desired signal x and the undesired interference v are uncorrelated. So the correlation matrix of the desired signal equals to the correlation of this is the measurement, the correlation matrix of the measurement. It's a summation of the correlation matrix for the desired signal and the correlation matrix for the interference, for the noise. And we assume that the rank of the correlation matrix for the noise is full rank, and the correlation for the desired signal is lower rank, maybe less than full rank. We will talk about it. Why do we need to do that? Okay? Because if this matrix is lower rank, it means that the desired signal is within a certain signal subspace. We will talk what is a signal subspace. So if the rank is lower here, it means that we can represent any signal in a smaller signal subspace, so we can remove or suppress anything outside this subspace, so we can suppress more noise. And we will talk about definitions and what does it mean. Okay, so linear filtering, it means that the output sample, the estimate after the estimation, is a superposition of the L samples from the measurements. So we can write it as H transpose in a vector form, H transpose Y, where H contains the weights that we give to each sample. So this is called linear filtering for estimation. By the way, if we use future samples of Y, here we use only past samples of Y in the past. So we have the current, and total we use L samples of the measurement. If we use future samples of Y, how do we call it? So instead of causal estimation, How do we call it? How do we, if we use future samples of y, what? Non-causal. So it's non-causal estimation. If we don't use the current sample of y, suppose that we don't have yt. We have only L samples, but in the past, without the sample at time t. How do we call it? Instead of estimation? Prediction. Exactly. Why? Because we don't have the measurement at time t. We want to estimate xt based on previous, only past samples, without the current sample. So we call it prediction. Okay? So we have different names, but and if the function is linear, so we call it linear. Linear filtering, linear prediction, and so on. If the function is any nonlinear function of the measurement, we call it nonlinear filtering, estimation, prediction. For example, if we use neural network to find the output, the estimator, based on some samples, and neural network is nonlinear, so we have nonlinear estimation, prediction, causal, whatever, all these names, okay? But here we focus on linear because it's simpler for the definitions and for understanding and for the intuition. Okay, so the block diagram looks like that. We have desired signal vector, L samples, noise. So we have here L samples of the measurement. We multiply it with certain weights vector, and we get an estimate of the sample xt. These are vectors. All these are vectors. This is a scalar, only one sample. Okay, so we can write the output. This is the output as H transpose X plus V. So it has two components because it's a linear filter. So this is the advantage, that we can define things more easily. So we have this sample contains two components. One component is the desired, is the filter desired component, and this is the residual noise, which is H transpose V. So ideally, we want to have the filter desired equal to the sample, the original signal of the clean signal. So ideally, what we want to have is H transpose xt equals, or we want it to be as close as possible to xt. Okay? This is what we want to have. Because this, what does it mean if it equals? It means that we have perfect estimate, no distortion, perfect estimate. And also, perfect estimation, it's not enough, because we can take y, if we take h, equals to 1, 0, 0. Do we obtain here equality? Yes, because we just take the first sample and the component here. So we have undistorted signal that is estimated. But we will have all the noise in the original signal. It's like we didn't do anything. With this filter, we didn't do anything. We just take the measurements as is without reducing the noise. So we want also the residual noise to go to 0 as much as possible. So we want to estimate the signal without distortion and suppress the noise. But of course, this is a trade-off. We cannot do both. So we can measure what is the variance of this, of the filter desired, and what is the variance of the residual noise. We want that the variance of this, or the error, to be as small as possible, and the residual noise to be as low as possible. So the variance of the estimate contains two components, the variance of the filter desired and the variance of the residual noise. From this, we can compute also the signal to noise ratio. So the variance of the filter desired is H transpose RXH, and the variance of the residual noise is H transpose RVH. Rx and RV are the correlation matrices of the desired and the noise. Okay? How do we get it? Very easily, you see? Because expectation of Z squared, we said that Z squared, Z is a scalar, which equals to H transpose Y. So we can write it like this, or we can write it Y transpose H. Okay? The same. Because here, so we can write expectation, the variance of Z, the variance of Z, we can write it as E. Now, it's better to write Z multiplied with Z, but differently. H transpose Y, Y transpose H. Okay? Even though we can write this as squared, but it's better to write it like this. Because like this, we can write it as H transpose RY H. And RY, because X and V are independent, so we can write it like this. Two components. You see, with linear filtering, everything is much simpler. So we can define the input signal to noise ratio. Input signal to noise ratio is actually, what does it mean? In the original signal. In the original signal, we have Y t equals to xt plus vt. So the input SNR is the ratio between the variance of x and the variance of v. This is the input SNR. And of course, we can write it as trace of Rx divided by trace of Rv. It's the same. Okay? What is the output SNR? So the output SNR is the variance. We said that Z, okay, Zt, which is the estimate of xt, is X filter desired plus V residual noise. So the output SNR is the ratio of the variance of X filter desired by the variance of the residual noise. So it's H transpose RXH divided by H transpose RVH. This is the output SNR. And what is the gain in signal to noise ratio after filtering? The gain in SNR is the ratio between output SNR divided by input SNR. Okay? So for example, I can ask you how to find H, how to find this vector such that the output SNR will be maximum, or the gain in SNR. You see, the input SNR is independent of H, is the input. But after the linear filter, the estimator, I can ask you, how do I find H such that the output SNR, or the gain in SNR, same, will be maximum? Which filter, which H, which filter maximizes the gain in SNR? How do I define it? So which H maximizes this ratio? Okay? So it's possible to solve it. Actually, it's not difficult. It's also possible to prove it. But there is a way to maximize this ratio. Okay? But I want to ask you, before we solve it, I will show you how to solve it, we'll talk about it, but it's more important to know what type of information do I use? What is the information do I use to solve this problem? Assume that I have Rx and Rv, right? Because once I have Rx and Rv, I can find the filter that maximizes the output SNR. What is the information contained in Rx and Rv? Okay? Think about it. I have one sensor. I have these measurements, sample after sample. I sample this single channel, measurements. So I have, what does it mean that I have Rx? It means that any two samples, such that any two samples that are distanced by the time less than L samples, okay? So if I take two samples from the vector X, you know, the vector L, the vector X contains the vector X contains the signals xt, xt minus 1, and so on, until xt minus L plus 1. So it contains the L recent samples of X. So if you take any two samples from this vector, I know their correlation, which is a lot of information. And I know this also for the noise vector. So I know Rv. So I know Rx and I know Rv. And based on that, I can find H that maximizes the output SNR. But this, in practice, is very difficult to know. Okay? So here, I assume that I know it. If I know it, I can find the filter that maximizes the SNR. But this, we will see some examples. It's a lot of information, and it's very difficult to know that. After we define the performance measures, we will find optimal filters that optimize things. Okay? So this is the identity filter. Just like I mentioned. If I have 1 and the rest is 0, if I take H equal to that, what happens? I don't do anything. So the output SNR will be the same as the input SNR, because I didn't change anything. I keep the original measurement as is. Do I have distortion in the original, in the measurements? No distortion. But I didn't do anything for the noise. I didn't reduce any noise. So the output SNR remains as the input SNR. Noise reduction factor. What does it mean, noise reduction factor? How much noise I have at the output compared to the input. So this is the ratio between the variance at the input, variance of the noise at the input, and variance at the noise at the output, at Z. So this ratio, we want it to be as high as possible or as low as possible. We want it to be high or low? High, exactly. High, it means that we reduced a lot of noise. The denominator, we want it to be as small as possible. It's the variance of the residual noise. We want this ratio to be very high. We can define also something similar, but instead of noise reduction factor, we can define desired signal reduction factor. which means what is the variance of the desired source at the input divided by the variance of the desired source at the output. So ideally, we want this to be ratio equal to 1, because we don't want to distort or to change or to reduce the desired. We want this to be closer as much as possible to 1. And then we think that there is no reduction of the desired source. And we have certain relations between the gain in SNR and the noise reduction and desired signal reduction factor. Okay, so it's very easy to show this ratio. We can also define distortion index, the desired signal distortion index. What does it mean? You see, the output of the filter contains 2 components. So we can ask, what is the error, the expectation of the error, between the filter desired and the original signal? So here we don't take into account the residual noise. We just care about the distortion, and it's normalized. So we have this expression. Okay, so from here we can move to here, and many times, okay, so we want that this distortion index, which is roughly between 0 and 1, it's normalized. We want to be as close as possible to 0. So we want to find H such that this expression is as close as possible to 0, which means that the signal is less distorted. Mean squared error, it means what is the error between the estimate of X and X. So it takes into account 2 components. One is the distortion, and one is the residual noise. So we want to minimize both components. One component is the distortion, which is related to the signal, and one is the residual noise. So the mean squared error takes into account both components. The mean squared error related to the distortion and mean squared error related to the residual noise. And we can say that we want to minimize both. Okay, and of course we have some relations between the ratio. So the ratio between the mean squared error related to the distortion and the residual noise, we have some relations between the performance measures, like this. Okay, so it's easy to show. And before we move on, so based on this criteria, we can find Someone asked me about references to constant beam width beamforming. Okay, so what you can do, we did some work on that. So you can use my website. Let me see if it's here. Okay, if you go to my website, it's israelcohen.com. Okay, israelcohen.com. So you can go to publications, journals. I don't have it here. Just a minute. Okay, so if you go to publications, journals, and actually if you write constant, I think you can get many publications about constant beam width and so on. But what I recommend is to go to this. This is a very nice paper, which is a window-based constant beam width beamformer. Actually, based on what we talked about beamforming, you can already read this paper based on your knowledge from what I wrote about the overview. And if you're interested, it will be a very nice way to see, because I assume you have the background for signal processing and you know about sampling and so on. So I recommend that you try to read this paper about constant beam width beamformer. So it was published, you see, in 2019. So even though it's 20 pages, many are the references and so on, I think you can try to read it and see if you understand. I think you are supposed to understand this paper already based on the overview, okay? Because it's a simple way to do, and it's much nicer than the subarray method that we used before. And if otherwise, afterwards, if you're interested and your research is related to such things, you can go to more sophisticated papers with constant beam width beamforming. For example, this is also a nice paper with constant beam width beamforming with concentric ring arrays, which is interesting. And we did also things with non-uniform sensor arrays and so on. But this one is quite simple, the first one, which I mentioned. Any other questions that you have so far? Okay, so let's continue. So we defined performance measures. Now we want to optimize, to find optimized filters in order to improve or based on this criteria. Okay, so the simplest or the most common optimal filter, it's known as Wiener filter. Wiener filter, what it tries to do is to minimize the mean squared error, what we defined before. So the mean squared error contains two errors. One, the error which is related to the distortion, and the other error is related to the residual noise. Okay, so we said that Z equals to X filter desired plus residual noise. So if we take Z minus X, and we take that squared. So this is the squared error. And if we take the expectation of this, this is the mean squared error. So this is the mean squared error, which depends on H, on the vector H. So the filter that minimizes this mean squared error is called the Wiener filter. And the question is if it's good or bad. So it depends on your application. Sometimes it's good, sometimes it's not good enough, because the mean squared error, it doesn't mean that the performance is good. It just minimizes the mean squared error. I can show you examples, either for speech signal or for images. You look at the image, the mean squared error of two images with one, the mean squared error is lower, but it looks worse than the other image. So not necessarily minimizing the mean squared error is the best option. Sometimes it depends on the application, because when you listen to music or when you listen to conversation, sometimes the criteria, or actually many times, the criteria are different. But this is a good way to start with minimizing the mean squared error. So the solution, in our case, it looks like this. So the question is, how did we find it? So I hope you're familiar with derivatives. So what we need to find is actually, if we go back to the mean squared error, you see? So this is the expression for the mean squared error, you see? So in this expression, we assume that we know the variance of x. This is the variance of the desired signal in the input. And we know our x. This vector I is the identity vector, which is 1 and all zeros. And this is our y. We know the correlation matrix for the measurements, for the y. So you see, if we take this expression, we find the derivative. This is a scalar, right? If we find the derivative of this expression with regard to h and equate it to 0, we find the solution that minimizes this mean squared error. So this is a good exercise, how to find the derivative of this and equate it to 0. Okay, so if you're not familiar how to find derivative of such things, let me know, because you can find this on the internet, different formula. And this is, there are certain rules how to find the derivative of a function of a vector, okay? If you're not familiar with that, it's very important to know these expressions. Okay, so the solution is like this. Ry minus 1, Rx, I. You see, so this is the vector, that optimal. Now this vector, we can write it differently. We can write that Ry, we know that Rx, based on our model, is Ry minus Rv. Okay? So we can write this. We know that Ry equals to Rx plus Rv. So we can put, instead of Rx, we can put Ry minus Rv. So we get this expression, where IL is the identity matrix of size L by L. So my question is, suppose that I implement the Wiener filter and I find it from here or I find it from here. Will it be the same solution? So what do you think? It looks like the same, right? Okay, so when is it the same? When I know Rx and Ry exactly. If I know them exactly, so these expressions are the same. But if Rx is estimated and Ry is estimated from observations, so generally these two forms will generate different results. Okay? Because what I wrote over there, that Ry equals to Rx plus Rv, it's true for the accurate or based on the model Rx and Rv. But if Rx and Rv and Ry are estimated, if I estimate Ry from the measurement, this is not true anymore. Generally, it will not be equal to Rx plus Rv. So if I estimate, for example, Rv from periods where I don't have X, I don't have the desired signal, periods in time that I have only the noise, even stationary noise. And then I have some measurements. And this I estimate from a certain length of measurements. It will not obey this. And therefore, these expressions, if I use estimates of Rx and Ry, will not generate the same results. By the way, here I need Rx. Rx, many times it's very difficult to obtain. So the advantage of using this is that Ry we estimate from the measurements, and Rv we can estimate during pauses in the desired signal. Because the signal is, sometimes it's limited, it's not present all the time, where the noise is usually present all the time on interferences. But as I told you, this is very important information that we use, and if we don't have this information, we need to estimate them. And the estimation of Rx and Rv or Ry depends on the application, and every different estimates of these matrices will generate different results, different performances. And this is a topic by itself. Okay? We can also normalize Rv, Rx. So these are the normalized correlation matrices. Normalized correlation matrices, and we can use them, and we can obtain different expressions for the Wiener filter. We can also write it using the Pearson correlation coefficient. So this is Pearson correlation coefficient, or the squared Pearson correlation coefficient, which actually it's normalized correlation between two signals. So if we have two signals, Y and V, so this is the square of the correlation divided by the variance of each one of them. So it's normalized. So it's in our case, it will be like this. So if we have a high signal to noise ratio, it means that this correlation will be higher or lower if we have high SNR. The more input SNR, the higher the input SNR. What will happen to this correlation coefficient? Higher or lower? Two options. I don't give like 10 options. Okay, only two options. So you can guess. You have 50% to succeed. Think Y equals to X plus noise. Okay? Y T equals to X T plus noise. So high input SNR, it means that this variance, X, is much larger than V. So the more they increase the SNR, it means that this ratio is higher. The variance of X divided by the variance of V is higher. So the correlation between Y and V will be higher or lower if we increase this ratio. Lower, okay? Okay, so we have a way to determine what is the signal to noise ratio. So instead of saying that the signal to noise ratio, the input signal to noise ratio is high, I can say that the correlation between the measurements and the noise is low. If I say that the correlation between the measurements and the noise is high, it means that the input SNR is low. Okay? What about the correlation between the measurements and the desired signal? So this is proportional to input SNR. If the input SNR is high, so the correlation between Y and X will be high. So this is the squared correlation coefficient, Pearson correlation coefficient, which is very useful. That's why you see here the relation between the squared Pearson correlation coefficient and the input SNR. You see, if the input SNR is high, it means that the correlation between the measurements and the noise is low. Makes sense. Okay, and for our example, it looks like that. This is the relation. But it's always true. It depends on the model. But here, it's 1 over 1 plus input SNR. So you can compute it. And what we can see that for the Wiener filter, if the input SNR goes to infinity, the Wiener filter goes to the identity filter, which is interesting. Because if the input SNR goes to infinity, it means that this is negligible, the noise is negligible. And then the Wiener filter goes to the identity, 1 and all zeros. It means that the estimate, Z, will be equal to Y. Makes sense. Because if the input SNR is very high, you don't need to do anything. It's better to keep the signal Z equals to Y, because Y doesn't contain much noise. But if the noise is significant, if the noise is significant, the input SNR goes to 0, so this is negligible. If Y equals to V. So H, the filter, goes to 0. Why? Because X is negligible. You don't have any desired signal. So it's better just to suppress the residual noise, because the mean squared error has two components. One is distortion, one is the residual noise. But the distortion is not important because you don't have X. It's negligible. So it's better just to remove or suppress the residual noise by equating the filter to 0. So you suppress everything because you don't have any signal over there. It's negligible. Okay? So these are sometimes when you derive something, you want to check that at the extremes it makes sense. The solution, your solution makes sense. So it's possible to check that. Okay. Another thing is, also it makes sense, we derived the Wiener filter that minimizes the mean squared error. This was our criterion. And we can ask ourselves, okay, we minimize the mean squared error, but what happens to the output SNR? Does it increase compared to the input SNR? Is the output SNR, so this ratio, the output SNR, the ratio from here to here, compared to the input SNR, is it larger or smaller? We didn't use any constraint or criterion based on the SNR. We just minimized the mean squared error. So it's very important to know, because if it reduces the signal to noise ratio, we need to think, why does it happen? Is it necessarily increase the signal to noise ratio? So it's possible to prove that the Wiener, you see, with the Wiener filter, the output SNR is always larger or equal to the input SNR. So we don't reduce the signal to noise ratio, which is important. It's possible to prove it. I will not go through the proof. You can read, and it's straightforward to see it, but it's an important feature that the Wiener filter does not reduce the output SNR, because the SNR is also important. So this is the proof. Okay. And we can find, or we can write the minimum mean squared error. So we can ask, okay, with the Wiener filter, the mean squared error comes to a minimum. So we can write the minimum mean squared error by different expressions. And we can see that any mean squared error that is obtained with any filter, of course, it will be larger or equal to the minimum mean squared error, because this was obtained with the minimum with the Wiener filter. And also we see that we have upper bound for the Wiener filter, because if we take here the identity, we have the variance of the noise, so it's obviously the minimum mean squared error is smaller or equal to the variance of the noise. So we can see, if we use the expression that we obtained for the Wiener filter, we put it in the expressions that we obtained for the output SNR, the noise reduction factor, the desired signal reduction factor, and the distortion index. We get explicit expressions for all of them. Okay? Let's see an example. It's always good to see an example. Suppose that we have this signal, xt equals to A cosine 2 pi f0t plus phi. A is a certain magnitude, amplitude of the signal, is a certain amplitude of the signal. And what happened? Let's see. Okay. I don't know what happened, but okay. So suppose that we have this signal, and suppose that the amplitude is constant, f0 is lower than the Nyquist frequency, so it's between minus half and half, because t is the sampling interval. We assume it's normalized. Okay, everything is normalized. So the sampling interval is 1. We normalize by the sampling interval. And so f0 is between minus half and half. And phi is the random phase, uniformly distributed on the interval from 0 to 2 pi. Okay? So this is the desired signal. And suppose that we measure this signal together with additive white Gaussian noise. And we get the measurements like this. And from the measurements, we want to estimate this signal. So actually, in practice, if we know this model, if you know the signal, and the signal has some parameters, it's better to estimate the parameters of the signal and not the signal itself. Okay? So usually it's called estimation of parameters. So we will estimate the amplitude, we will estimate the frequency, and we estimate the phase. But here I assume that I don't want to estimate the parameters. I want to estimate the samples of the signals x from the measurements using the signals, using the Wiener filter. Okay? Obviously, I will get degraded performance but I want to show you how to use the Wiener filter. Okay, so what do we mean? So if we take this signal and we have white Gaussian noise with variance sigma v squared, this is the input signal to noise ratio. You see the expectation. The only random variable is phi. This is random phase. So if we take the variance of xt is a squared divided by 2. So this is the input SNR. And we can also find the correlation matrix RV for the noise, which is sigma v squared multiplied with the identity matrix, L by L. So it's very easy. Why? Because it's white noise. White noise, it means that any element on this matrix outside the diagonal is 0. For white noise, it means that any two samples, which are not the same sample, okay? Any two different samples in the vector V are uncorrelated. That's why in the correlation matrix it will be 0. And along the diagonal, because it's the same variance, so we have sigma v squared. So this is the correlation, which is very nice here, because if we know that the noise is white, we put zeros except the diagonal, and along the diagonal, if the noise is stationary, so we can put the same value, and we can take certain measurements of the signal when maybe we don't have the desired signal, so we can estimate sigma v squared. Or maybe we know sigma v squared, so we put it here. So to estimate or to find RV, it's quite easy, right? In this example. Now, if we want to find Rx, Rx is more complicated. Okay, so maybe you can find Ry and subtract Rv from Ry based on samples of the measurements. This is one possibility. But here we choose another possibility, so which is based on, suppose that we know A and F0. We know the amplitude and the frequency of the signal. Usually we don't know that, because if we know that, we can estimate xt by only estimating the phase. But for the purposes of finding Rx, if we know A and F0, then this is an element ij in this matrix. So if I take two samples of Rx, of xt, and I take the expectation, because the phase is random, so this will be the expectation. Okay? So prove that. Okay? So I will give you today an assignment in this example. Based on this example, you will get an assignment. So I want you to understand this. So first, prove that I can find the elements. And also, suppose that I don't know A and F0, and I want to estimate this matrix from Ry. So I can find based, it's stationary. So I can take certain interval of yt, and based on examples of RT or the samples of RT, I can find any element of Ry, and then subtract from that Rv and obtain Rx. It will be different. Okay, so I want you to repeat this example and try these differences. I will continue. You see, it's not that easy even for that very simple example. Okay. And so for this example, I take A equals to half, F0 equals to 0.1, which is less than the Nyquist frequency. And sigma V squared is 0.3. So the input SNR is minus 3.8 dB. Okay? First, I'll show you what is the gain in SNR. The gain in SNR, which is the output SNR divided by the input SNR, that is obtained for different L. What is L? Remind me, what is L? The number of samples that I used for filtering. You see here, the number of samples that I used for filtering. So what I see here, that if I increase the number of samples, I improve the SNR. And I also, the minimum mean squared error using the Wiener filter decreases. This is very nice. It means that the more samples that I use, I improve both the mean squared error, it decreases, and the gain in SNR, it increases. Which is interesting. Is it always true? So why do we get here improved performance, gain in SNR and MMSE? The main reason is that we used Rx and Rv. We used the true matrices, So because these are the true matrices, when we increase L, we have more information. Because we know that within this vector of length L, we know the correlation, the true correlation between any two samples. And this is a cosine signal. So cosine, we know exactly the correlation between any two signals for a certain length L vector. So we have more information. If we increase L, we have more information. So we can estimate xt better. You see, that's why it increases. And this is decreases. Very well. But suppose that you don't know the true Rx and Rv. You estimate it from a certain length, and you don't increase this length. What do you think? What will happen if we increase L? It will not necessarily increase. To some degree it will increase, but afterwards it might even decrease. Why will it decrease and not be plateau, or we stay at a certain level? Why do you think it may even decrease? Think about it. If the question is not, if you don't understand anything in the question, let me know. I will explain. Okay, so what I claim, that if we use the true Rx and Rv, the performance when we increase L increases because we use more information. But if we don't use the true Rx and Rv, we estimate it based on a certain length. The length of the signal Y is fixed because we have a certain length of information of samples that we use. 1 second, 2 seconds, 5 seconds, maybe 1 minute. And from that measurement, we estimate Rx and Rv. And then we increase L. So I claim that it increases, but maybe afterwards it may even decrease. Why will it may decrease? Yes. So what do you mean? So why will it may decrease? Okay, yes. So when I increase L, I put in the matrix Rx correlation between samples that are far from each other. And then I use this information. And maybe this information is misleading. It's wrong. You see, so when I use correct information, correct matrices, correct correlations, I increase the L, I have more information. But if I give you additional information, but it's wrong, because the estimates of these correlated signals which are far, maybe it's incorrect, then you will get error because of this wrong information, wrong estimate. You see, it's better not to use wrong estimates than to use it. Additional information, it's not always good. If the information is wrong, we don't know whether to use it or not, and we use the wrong information, so it leads us to wrong estimates. Okay? And this is well known in estimation theory, that when you use additional information and it's wrong, it's misleading, you get degraded results. So this is a very interesting. If you like, you can check it. Okay? So try something like that. Take a certain length of the signal and try it. So I will give the assignment soon, and I will talk about what is required. Okay, and here we get the output SNR, function of input SNR, and the MMSE as a function of input SNR. You see that the input SNR increases. Of course, the output SNR also increases, and the minimum mean squared error decreases. This is obvious because we have less noise. And these are the noise reduction factor when we increase the input SNR and the distortion. So we see the noise reduction factor decreases. It makes sense because we have less noise, so we need to reduce less noise, and also we have less distortion, and also the distortion here, the distortion decreases when we increase the input SNR. This is a realization of the signal. So suppose that we have a certain length. We have 500 samples of a noisy signal. For that, this is a realization, and this is the result of Wiener filtered signal. So first, because we apply Wiener filter, you see we don't estimate the amplitude and frequency and separately, and the phase. So we get whatever we get. So it's the envelope here is noisy. It's not like one amp, and the frequency can change along the signal, and also the phase maybe it's inaccurate. But this is the signal that we get. At least it's better. The signal to noise ratio is higher. This is a realization. Input SNR equals to 0 dB. What is your assignment? So please work on this assignment. I'll give you 4 assignments. Every 2 days, you get an assignment. Assignments are very important, not for the grade. It's just to practice, to see what you understand, what you don't understand. Okay? So first you have some things to prove, to show the mean squared error, some relations that we showed. It's very easy to show these relations. Another, so this is 1, another one is 2, is to show that taking the gradient of the MSE gives you this solution. And if you're not familiar how to take gradients of scalar with respect to vectors, you can find a formula on the internet. You will need that for array processing, image processing, deep learning. So it's better to learn that as soon as possible, okay? Very useful to use this formula. And to understand, if we take a gradient of a scalar with respect to a vector, the result is a vector. If we take a gradient derivative of a scalar with respect to a matrix, the result is a matrix. How it is defined. If we take derivative of a vector a function which is a vector with respect to a vector. The result is a matrix. Okay? So all these, what are the definitions? How do we define it? What is the element? What is each element of this matrix? So this definitions and how to find the optimal optimality vectors or filters and so on. This is like linear algebra. It's very useful in signal processing and machine learning. So people who are not familiar, please look at the internet on the formula, and I promise you that it's very easy, but you need to learn that. Okay, so here, prove the derivative. This is the solution. Number 3, show that the Wiener filter can be expressed like this, based on the squared Pearson correlation coefficient. Okay, so these 3 problems are very easy, just to see that you understand, very basic. Here, the first one, this is using MATLAB, so it may take you more time to work on that. That's why I want you to use MATLAB code from my website. Okay, so I want you to generate the figures in example 1, all these figures that we just saw, but with different parameters. Change the parameters, play with that. But I don't want you to spend now 3 days on that, okay? So I want you just to play with the code, the MATLAB code, change some parameters, understand, and submit something with different parameters, and also explain what you did differently and why did you obtain or you got different results with the different parameters, different estimation. You have time to play with that. It's up to you. Okay, and the figures, the figures in this book that I wrote, I'm co-author. So it's the figures are different. So you can download the MATLAB code for all the figures in the book using my website. Here, you go to my website and you go to publications and you go to books. Okay? So if you go to books, I have the books that I wrote. So this is the book for this course. And here you have partial solution manual for some of the problems, if you like. And also you have a MATLAB code for all the figures in the book, MATLAB code. So you can download it here. And then you need to know which figure in the slide correspond to which figures, because it goes according to the numbers of the figures in the book. So I tell you here that figures 2 to 5 in the slides correspond to figures 2.2 until 2.5 in the book. So when you download the MATLAB code, they correspond to this. For each figure, you have a MATLAB code. So you can play with it, okay? And then you generate different. So it's up to you how much time you invest on that. Any questions on the assignment? By the way, even beyond the assignment, things that you are not sure how to derive different expressions. So please try to prove it. Okay? And afterwards, so tomorrow, I hope you do the assignment today, because it's important when it's material fresh. If you don't have time today, it's also possible to do it partly tomorrow. But I want you tomorrow to tell me if something doesn't work, if you don't ask questions. Okay. And afterwards, we will talk about different filters, which are also important. We will talk about trade-off filter, NVDR, and maximum SNR filter. So trade-off filter, we will see, because the mean squared error, if we try to minimize the mean squared error, actually we minimize both the distortion and the residual noise. But sometimes we want to reduce more distortion on the account of increasing the residual noise, and vice versa. So we want some trade-off between distortion and noise reduction. So we will talk about trade-off filter. And then we will talk about MVDR filter. Remember, we talked about minimum variance distortionless response beamformer. We will use it. So we will show what is MVDR filter. What does it mean, MVDR filter? It means that we want that X filter design will be equal to X, no distortion. And then we want to minimize the variance of the residual noise. This is MVDR filter. And we will see when we come to multi-channel signal processing, we will see the relation between MVDR filter and MVDR beamformer, or multi-channel MVDR. That's why we want to see it here. We will also talk about maximum SNR filter. We see that the MMSC filter, the Wiener filter, does not reduce the signal-to-noise ratio. But if we take the criteria, if we look for the filter that maximizes the output SNR, how different, what is the relation between the filter that maximizes the output SNR compared to the Wiener filter? Which one is better? Which one is better? The maximum SNR filter or the Wiener filter? Maximum SNR or min? Okay. So this is, you know, sometimes question is misleading question. It's whatever you say, it's not the correct question, the correct answer. Why? Because when I ask you what is better, you need to ask me according to which criterion, okay? So according to the minimum mean squared error criterion, Wiener filter is better. But according to the maximum SNR criterion, maximum SNR filter is better. So whatever is better, it depends on the performance measure. How do I measure what is better? And when I measure what is better, according to this criterion, I find the optimal filter, the same like multi-channel and so on. By the way, when you listen, suppose that I record speech in a noisy environment. Suppose that I show you pictures, and I show you a few pictures, and I ask you which picture is better. Or when you listen to signal, you listen to music, and I ask you which signal do you think is better? Okay? So there is something which is called mean opinion score. Mean opinion score. So this is many times subjective criterion. Subjective criterion that we try to optimize. We say that we listen to a signal, but then we need to take many people, large number of people to listen to signals or to see the pictures and so on. And we teach them to give grade to the signals. Sometimes the grade is 1, 2, until 5. 5 is the best, 1 is the worst. And then if we take a large number of people and they listen to the same signals or watch the same pictures or video or whatever, and we train them, we teach them how to give a grade, 1 or 2 or 5. Because if we don't teach them, they don't know that this signal, maybe it's 4 or 2, I don't know. but if we train them how to give this grade, and then we take the average grade for a large number of persons, it's called mean opinion score. So it's subjective. And many times we want to optimize this. For example, if I give somebody picture of X-ray, chest X-ray, and ask him, is it this picture or this picture? Both X-rays of persons, chest X-ray. Which one is better? But you don't understand which one is better. You need to be a doctor, or you need to be familiar with that. So you need to train which one is better and to get this opinion score. So you see, performance measures depend on the application. And when we try to optimize it, it's not easy. Here, because it's mathematically well defined, we find the solution. So we will continue here with the other filters tomorrow, and then we will proceed. Okay? So any questions so far? Okay, so have a nice rest of the day. Enjoy the rest of the day. Enjoy the assignment. If you have questions, let's talk about it, about the assignments further. Let's talk about it tomorrow. So you have 2 days to finish that and attend the material. Okay? Thank you. See you tomorrow. And by the way, if you have any comments about the seed pace, you want to change something, please let me know. Okay? Because it's important so I can adapt. The goal is that you understand the material and enjoy and have some intuition, and not to keep and to review more material. It's not my objective. Okay? So I would like to know. Thank you.